Right now, before the explanation begins, do this. Make a fist with both hands, not loosely, not performatively, as hard as you can, and hold it for 10 seconds. Feel the muscles of the forearm tighten. Feel the tendons pulling against the bones of the wrist. Feel the blood pressure building in the hand as the vessels are compressed by the surrounding muscle. Now release. All at once. Feel what happens in the 2 seconds after that release. There is a spreading warmth. A slight tingling at the fingertips. A diffuse ease that moves up the forearm and, if you held tightly enough, into the shoulder. What you are feeling is not the relief of releasing tension in the way you release a gripped steering wheel or unclench a jaw. It is a specific neurological event, a measurable, reproducible shift in the state of your autonomic nervous system, triggered by a mechanism that your nervous system has been using to regulate itself for hundreds of millions of years. The squeeze was not the intervention. The release was. And what the release produced in your brainstem and spinal cord is something that took neuroscience most of the 20th century to understand, and which still does not appear in the morning routines of most people who spend considerable effort managing their health and stress. The mechanism has a name. It is called post-isometric relaxation. And it is only the first layer of what just happened. The autonomic nervous system operates in two primary modes. The sympathetic division, the system responsible for the fight or flight response, accelerates heart rate, dilates the pupils, redirects blood flow from the viscera toward the skeletal muscles, raises cortisol and adrenaline, and tenses the muscles of the trunk and extremities in preparation for physical action. The parasympathetic division, the system responsible for rest, digestion, tissue repair, and immune function, does the opposite. It slows heart rate, stimulates digestive secretion, promotes cellular repair, and reduces the tonic tension held in skeletal muscle. These two divisions are not simply opposites. They are two halves of a dynamically balanced regulatory system, and their balance at any given moment determines, with remarkable precision, what your body is doing at the molecular level, whether it is building tissue or breaking it down, whether it is mounting an inflammatory response or resolving one, whether it is consolidating memory or interrupting it. The autonomic balance is not fixed. It shifts across the day in response to stimuli. And the skeletal muscle system is one of the most direct interfaces through which the nervous system can be pushed from one state toward the other. The mechanism of post-isometric relaxation was described with precision by Vladimir Janda, a Czech neurologist and rehabilitation physician, whose work on muscle function and dysfunction in the 1960s through 1990s established the foundational framework for understanding how the motor and autonomic systems are cross-coupled. What Janda observed, and what subsequent neurophysiology has confirmed through the identification of the specific neural circuits involved, is that a maximal voluntary contraction of a skeletal muscle, held for 6 to 10 seconds, followed by sudden complete release, produces a period of enhanced muscle relaxation that is significantly deeper than the resting baseline. This is not the relaxation of passive stretching. It is not the gradual relaxation of holding a static stretch for 30 seconds. It is a neurologically mediated suppression of motor neuron excitability that occurs through the activation of Golgi tendon organs, mechanoreceptors embedded at the musculotendinous junction that fire when the tension through a tendon exceeds a threshold, which send inhibitory signals via IB afferent fibers to the alpha motor neurons supplying the same muscle. The Golgi tendon organ is, in this context, a tension overload protection system that the body activates during maximum contraction to prevent tendon avulsion. When the contraction releases, the inhibitory signal persists for several seconds. The motor neuron is, briefly, actively suppressed below its resting excitability level. The muscle cannot return immediately to its previous level of tonus. It drops lower. This window, this brief period of motor neuron suppression, is the mechanism, and the autonomic system is reading it in real time. The relationship between skeletal muscle tension and autonomic state is not metaphorical. It is anatomical. The neurons that control muscle tone and the neurons that regulate sympathetic outflow share synaptic territory in the ventral horn of the spinal cord and in the reticular formation of the brainstem. Antonio Damasio at the University of Southern California, building on decades of earlier work by Charles Sherrington and then by Walter Cannon, established through lesion studies and neuroimaging that the brain continuously uses the state of the body, including the tension state of the skeletal musculature, as input for determining and regulating internal homeostatic state. This is the somatic marker hypothesis in its most mechanistic form. The body's physical state is not merely a readout of the brain's emotional and autonomic output. It is an input that the brain uses to estimate and adjust that output. A body in high tonic muscular tension signals to the brainstem structures that regulate sympathetic tone, the locus coeruleus, the dorsal raphe nucleus, the parabrachial nucleus, that the organism is in a state requiring arousal and threat readiness. A body in which skeletal muscle tension drops suddenly and globally, through what happens in the 10 seconds after you release a maximal fist, signals the opposite. The reticular activating system, which is the network of neurons in the brainstem responsible for regulating the general level of central nervous system arousal, receives continuous proprioceptive input from muscle spindles and Golgi tendon organs throughout the body. This is the ascending reticular activating system pathway first mapped by Maruzzi and Magaun at Northwestern University in their landmark 1949 paper in Electroencephalography and Clinical Neurophysiology, which established that the brainstem reticular formation directly modulates cortical arousal. What their work established, and what has been refined through subsequent decades of neurophysiology, is that the flow of proprioceptive information from the periphery is one of the primary inputs maintaining the reticular formation in its alert, high arousal state. This is not a minor or secondary input. In the CAT preparations that Maruzzi and Magaun used, cutting the ascending proprioceptive pathways to the reticular formation produced a state in the cortex indistinguishable from sleep. The peripheral muscular state is not downstream from the brain's arousal level. It is a direct upstream regulator of it. When you perform a 10-second maximal isometric contraction and then release, you are generating a brief, powerful burst of IB inhibitory signaling that propagates through the spinal cord and upward into the reticular formation. The reticular formation, receiving a sudden drop in proprioceptive excitatory input from the peripheral motor system, responds with a transient reduction in ascending arousal. Heart rate slows. Sympathetic outflow decreases. The prefrontal cortex, which is suppressed by high sympathetic arousal and restored by parasympathetic tone, receives more blood flow. This happens in the 2 to 5 seconds following the release. The warmth and tingling you felt in your hand at the start of this was the vasodilation that follows reduced sympathetic vasoconstrictor tone. The ease you felt moving up the forearm was the motor neuron suppression propagating through the spinal interneuron networks. The slight deepening of your breath that most people report after the release, without having been asked to breathe, that is the brainstem respiratory centers responding to the reduction in reticular formation drive. None of this required intention. None of it required belief. It required a 10-second squeeze and a sudden release. But the release is only the first mechanism. There is a second operating through a completely different system, and it begins in the first second of the contraction itself. Isometric contraction, muscle contraction without joint movement, produces a specific pattern of metabolic byproduct accumulation in the working muscle that does not occur during isotonic exercise. When you make a fist and hold it maximally for 10 seconds, the muscles of the forearm and hand are contracting without shortening, compressing the intramuscular blood vessels and reducing perfusion to the working fibers. The muscle is generating force using ADP, adenosine triphosphate, which is broken down to ADP and inorganic phosphate. It is consuming oxygen faster than the compressed vasculature can deliver it. Within 3 to 5 seconds of maximal isometric contraction, the muscle fibers in the most compressed zones shift to anaerobic glycolysis, producing lactate and hydrogen ions. These metabolic byproducts, particularly potassium ions which accumulate rapidly in the extracellular space during intense contraction, and adenosine, which is released from working muscle cells when ADP is depleted, are detected by a specific class of small-diameter sensory nerve fibers that innervate the muscle, group 3 and group 4 muscle afferents, also called muscle metaboreceptors. These receptors fire in response to the metabolic state of the muscle, not the mechanical state but the chemical state. They are reading the chemistry of effort. The signal from group 3 and group 4 afferents travels to the dorsal horn of the spinal cord and from there to the nucleus tractus solitarius in the medulla, one of the primary integration centers for visceral and cardiovascular autonomic control. Mark Kaufman at UC Davis and Jerry Mitchell at the University of Texas Southwestern Medical Center conducted extensive work through the 1980s and 1990s mapping the exercise pressor reflex, the cardiovascular response to muscle metaboreceptor activation, establishing that activation of group 3 and 4 afferents by muscle metabolites directly drives increases in sympathetic cardiovascular outflow during exercise. This is the mechanism by which your heart rate and blood pressure rise during physical exertion, not through some slow hormonal cascade, but through a direct afferent to autonomic reflex arc with a latency of under 1 second. The muscle senses its own metabolic state. The brain responds immediately. The cardiovascular system adjusts. Now here is the part that is less well known. When the isometric contraction releases, the metabolic byproducts that accumulated during the compressed, ischemic phase are suddenly flushed out by the restored blood flow, a phenomenon called reactive hyperemia. The vessels that were compressed by the contracting muscle dilate reflexively in response to the same metabolites, particularly adenosine and nitric oxide, which are released by hypoxic endothelial cells and act on vascular smooth muscle to produce vasodilation. The flow-mediated dilation that follows a brief isometric contraction is measurably greater than baseline, a phenomenon documented in the peripheral vascular literature and, more recently, in the context of isometric exercise for blood pressure reduction, by James Goldie, Gil McInerney, and Jonathan Howley in the meta-analysis published in the British Journal of Sports Medicine in 2023, which pooled data from more than 40 randomized controlled trials and found that isometric handgrip exercise, specifically 4 2-minute sets of handgrip contraction at 30% of maximum voluntary contraction, performed 3 times per week, produced a mean reduction in resting systolic blood pressure of 8.24 millimeters of mercury. This is a larger effect than aerobic exercise, larger than dynamic resistance training, and comparable to a first-line antihypertensive medication. From squeezing a handgrip device. The mechanism is the reactive hyperemia and the shear stress-mediated endothelial adaptation. The repeated cycles of vessel compression and release train the endothelium, the single-cell layer lining every blood vessel in the body, to produce more nitric oxide at rest, reducing vascular resistance systemically. The muscle metaboreceptor reflex, during the contraction, briefly activates the sympathetic cardiovascular system. The reactive hyperemia, during the release, trains the parasympathetic and endothelial systems in the opposite direction. The net result, over time, is a recalibration of the set point at which the cardiovascular system operates. The squeeze does not just reset the nervous system in the moment. It trains the system to rest lower. And here is where the story changes, because the third mechanism operates not in the spinal cord or the medulla but in the cortex. And it begins not during the contraction but several seconds after the release. The prefrontal cortex, the anterior portion of the frontal lobe, comprising Brodmann areas 9, 10, 11, 45, 46, and 47, is the most recently evolved region of the human brain and the most sensitive to perturbations of autonomic state. It is the region responsible for working memory, emotional regulation, decision-making under uncertainty, and the suppression of impulsive responses from subcortical threat detection circuits, particularly the amygdala. The prefrontal cortex is also the region most rapidly degraded in function by elevated sympathetic arousal and cortisol. Arnson and colleagues at Yale University School of Medicine have mapped the molecular mechanism of this degradation in precise detail. Norepinephrine and dopamine, which are released at high levels in states of stress and high arousal, act on postsynaptic alpha-1 adrenergic and D1 dopamine receptors in the prefrontal cortex to suppress the firing of the pyramidal neurons that carry out the working memory and executive function computations. At low to moderate levels of these neurotransmitters, prefrontal function is enhanced. At high levels, the levels associated with sustained sympathetic activation, prefrontal function is suppressed. This is why decision quality degrades under stress, why emotional regulation fails when you are sleep deprived, why the thing you knew you should say in an argument is never what you actually said. The prefrontal cortex was taken offline by the sympathetic state before you got there. The post-isometric drop in sympathetic tone, the transient reduction in reticular formation drive that follows the 10-second release, produces a brief window in which the norepinephrine and dopamine tone in the prefrontal cortex shifts from the suppressive high arousal range toward the facilitatory moderate range. This is not a large or sustained effect from a single contraction. It is a window. Arnson's own data on the dose-response relationship between catecholamine levels and prefrontal function shows a steep inverted U-curve. Too little norepinephrine and prefrontal circuits are underactivated. Too much and they are suppressed. The transition between suppression and facilitation can be crossed by a relatively small shift in sympathetic tone. A 10-second maximal isometric contraction and release produces exactly the kind of brief, sharp downward perturbation of sympathetic activity that can push the system across that transition. The effect lasts, by most accounts in the related autonomic literature, for 30 seconds to perhaps 2 minutes. It is not a reset in the sense of a permanent recalibration. It is a window. And what the window opens onto, if used immediately, is a brief period of heightened prefrontal availability, reduced amygdala dominance, improved working memory capacity, slightly better access to the slower deliberative cognition that the prefrontal cortex specializes in. This is the science that is not in morning routines. Not because it is obscure. because it has not been assembled into a single coherent picture in a form that is accessible outside the specialist literature. Now I want to think about the morning timing, because the morning is not an arbitrary choice for when this intervention is most mechanistically relevant. Cortisol follows a precise circadian rhythm. Its concentration in the blood is at its lowest point during the first few hours of sleep, reaches its nadir at approximately 2 to 3 a.m., and then begins rising sharply in the hour before waking. The cortisol awakening response. A rapid spike in serum cortisol that occurs in the 30 to 45 minutes following waking, documented across multiple populations and measured by Pressner and colleagues at McGill University in studies published through the late 1990s and early 2000s, produces an increase of 50 to 160% above pre-awakening baseline levels within the first half hour of consciousness. The cortisol awakening response is driven by the HPA axis, the hypothalamic pituitary adrenal axis, and is modulated by the same anticipatory threat appraisal systems that determine how a person will orient psychologically to the upcoming day. People with high work-related stress, people with anxiety disorders, people who wake with an immediate cognitive orientation toward problems and demands, show exaggerated cortisol awakening responses. The amygdala, which is evaluating threat before the prefrontal cortex has fully come online. In the first minutes of waking, prefrontal inhibition of the amygdala is reduced because the prefrontal cortex requires longer to achieve full functional activation than subcortical regions, can establish a sympathetic tonal baseline for the entire waking day in the first 15 minutes after consciousness returns. This is the window that the morning squeeze targets. The cortisol is already elevated. The sympathetic system is activated. The amygdala is running ahead of the prefrontal cortex. A 10-second maximal isometric contraction, performed within the first few minutes of waking, generates the IB inhibitory cascade in the spinal cord, the drop in reticular formation drive, the reactive hyperemia in the peripheral vasculature, and, most relevantly in this moment, a brief downward perturbation of sympathetic tone at precisely the point in the cortisol awakening response curve where the system is most plastic and most responsive to recalibration. The intervention is not working against an already established sympathetic state. It is working at the leading edge of the day's autonomic trajectory, before the state has been locked in by the first 20 minutes of conscious threat appraisal. The timing is the intervention. Here is the part of this story I find worth dwelling on. The Golgi tendon organ, the mechanoreceptor at the center of this entire circuit, is one of the oldest structures in the vertebrate nervous system. It is present in lampreys, in sharks, in frogs, in every vertebrate that has skeletal muscle connected to tendon. Its primary evolutionary function is not nervous system regulation. It is injury prevention. It fires when a tendon is about to be overloaded, sending the inhibitory signal that prevents the muscle from generating enough force to tear its own attachment from the bone. The autogenic inhibition reflex, the name for the IB afferent inhibitory pathway, is a self-protection mechanism built into the architecture of muscle and tendon that predates the mammalian nervous system by several 100 million years. The fact that this mechanism, in humans, also provides a direct afferent input into the brainstem reticular formation that regulates cortical arousal, and that it can be deliberately activated by a 10-second voluntary contraction to produce a measurable shift in autonomic state, was not part of the evolutionary design. It is an emergent property of the way nervous system architecture was assembled over time, a safety circuit for muscle tissue that, in its modern incarnation, doubles as a regulation pathway for the most complex nervous system that has ever existed. Charles Sherrington, who won the Nobel Prize in Physiology or Medicine in 1932 for his work on the integrative action of the nervous system, spent decades mapping the reflex arcs that connect the peripheral motor system to the spinal cord and brainstem. His 1906 monograph, The Integrative Action of the Nervous System, written during his tenure at the University of Liverpool, is the foundational text for understanding how the spinal cord coordinates and integrates peripheral sensory input to produce organized motor and autonomic responses. Sherrington described the Golgi tendon organ, named by him after the Italian histologist Camillo Golgi, who identified the structure morphologically in the 1880s, as operating within what he called the proprioceptive system, the system by which the body knows its own position and state in space. What Sherrington could not have known, because the retrograde tracing methods that map neural connections from the spinal cord to the reticular formation and from there to the hypothalamus and the limbic system were not developed until decades after his death, is how deep into the brain the proprioceptive signal travels, and how fundamentally it modulates the state of every structure it passes through on the way up. The ascending proprioceptive signal from a 10-second isometric contraction and release is not a whisper. It is a shout, A synchronized burst of IB afferent activity from multiple muscles simultaneously, propagating up through the dorsal horn, synapsing in the nucleus tractus solitarius, reaching the parabrachial nucleus and the locus coeruleus, arriving at the thalamus and from there to the insular cortex and the anterior cingulate cortex. The regions that constitute the brain's interoceptive network, the system that continuously monitors and updates the brain's model of the body's internal state. The interoceptive cortex does not receive this signal as noise. It receives it as a state change. The body just reported, loudly, through the most ancient sensory channel it has, that tension has released. The brain believes the body. That is what resets the nervous system. Not the squeeze. Not any specific chemical or hormone produced by the contraction. The release. The sudden, global reduction in peripheral tension that propagates from the Golgi tendon organ through the spinal cord through the brainstem through the thalamus to the interoceptive cortex and tells the most ancient threat monitoring systems in the human nervous system what no amount of cognitive effort, no act of will, no decision to feel differently can reliably produce. A physical signal, not a thought about the body, but a signal from the body that the state of danger has passed. You did it at the start of this. You squeezed for 10 seconds and you let go. You felt the warmth at the fingertips and the ease moving up the forearm. What you were feeling was the IB inhibitory cascade reaching your spinal interneurons. The reactive hyperemia opening your peripheral vasculature. The reticular formation receiving the drop in proprioceptive drive and reducing its ascending arousal signal to the cortex. The prefrontal cortex, briefly, gaining ground on the amygdala. 10 seconds. Every morning. Before the phone. Before the news. Before the cortisol awakening response has fully committed itself to the day's trajectory of threat and demand. The nervous system does not need convincing. It needs a signal it already knows how to read.